Hi, my name is Daria, and I'm a part of the Exactpro research team. I welcome you at the Exactpro Systems YouTube channel and at Lecture 4 of our course on testing complex intelligent systems and autonomous vehicles. We'll start with a brief overview of the lecture. I will start with advising you on some additional sources we've put together on the subject. Then we'll try to define testing, quality, defects, and failures. Also, we'll talk about what testing is not, and that is quality assurance and module or unit testing, BDD. We'll also touch upon what bad testing is. Then we shall cover testing principles, types of testing, test objectives, and see what good testing is. After that, we'll talk about testing components, processes, platforms, and people. And lastly, we'll see if failures occurring in production are the tester's fault. Exactpro is a leading provider of software testing and related development services for financial market infrastructures. Our company was founded on the 9th of September, which is the Software Testers Day. We are headquartered in London with the rest of the offices scattered across the globe. Our company specializes in development and implementation of high-load market infrastructures, as well as systems that work with financial tools and platforms. Our solutions are used in more than 20 countries all over the world. Software testing is very complex and highly nuanced. There's a plethora of materials written on the subject, and it's nearly impossible to encompass the basics of testing in one lecture. I'm going to start by recommending several sources that will help you learn more about the topic at hand. One of the courses we recommend is Black Box Software Testing of the Context-Driven School of Testing. In fact, several ideas for this lecture were borrowed from those lectures. We also suggest that you check out the classes called Foundations and Bug Advocacy. A more concise version of the testing basics is available in the ISTQB Software Tester Foundation level syllabus. They say there's a disagreement between those who advocate for the context-driven school of thought and those who prefer ISTQB. But to form your own opinion, you should definitely learn about both. You can also go to the Exactpro Systems YouTube channel, where we have a video course on ISTQB. Let's not forget tons of interesting blogs and articles by the specialists working in the field. Michael Bolton is one of them, and we're going to quote some of his ideas during today's lecture. We can also recommend reading James Buck's blog. Here's a link to Yegor Bugayenko's presentation about quality assurance versus testing. Speaking of good testing, I would like to recommend Ingo Philip's excellent article on excellent testing, where he goes over 18 characteristics of excellent testing, plus gives more than 50 useful quotes about testing. Sometimes a picture is worth 1,000 words, so check out Andy Glover's blog. Andy Glover is also known as a cartoon tester. Now, moving on to the definition of testing. Software testing is extracting information about software quality. Software testing is a process of relentless learning, and therefore it's filled with pain and hard work. As we've described in the previous lecture, software testing consists in a closely intertwined network of processes, platforms, and people. A while ago, we shot a fanfic movie called Test World, which is based on Westworld, a popular HBO TV series. The original show is about the rise of machines and is chock full of quotes about robots becoming self-aware and also about testing. One of the key undertones of the series is the idea that to learn something, a human or a machine needs to experience pain and tragedy. A tragedy here stands for experiencing the world around us in a way that's different from what we want it to be. This makes us feel hurt and reluctant to go through something like this again. What's important is that painful experiences make us learn. We learn ways to avoid repeating the same mistakes and feel hurt again. So the mechanism of software testing is very similar to experiencing pain and relentlessly learning how to avoid it further on. That's a bit dark, isn't it? Nonetheless, we hope you will follow the link to see our Test World video. On a more general scale, Ray Dalio's book called Principles is very relevant to our topic. This slide has an excerpt from it which tells us pain plus reflection equals progress. When we bump into something that doesn't work the way we want it to work, we can reflect on it and reevaluate it, so it will lead to improvements. This is true not only in the world of software testing, it works in every aspect of our life. The first principle that Ray Dalio goes over is the principle of reality. It states that we have to accept reality and live with it. The truth and the accurate understanding of reality is the essential foundation of any truly worthy outcome. They are professionals who dedicate themselves to collecting true information and disseminating it. Let's take scientists. They study everything that surrounds us, be it immense in scale or microscopic, painting a picture of true reality for the rest of us. Another example is journalists. In its true sense, journalism means looking into something that doesn't fit, something extraordinary, which makes the news, and painting an objective picture of the occurrence. What's the difference between examples 1 and 2 according to the Scientific American Journal? While journalism is communication of what's new, science is communication of how the world works. Scientists tell the reader that they try to understand the reality around us, and now they're telling us how the world around us is built, backing it with proof. Similarly, investigators examine the crime scene, trying to deduce what has happened, again based on the evidence. Finally, software testers. They also excavate their designated field to unearth specific knowledge about the software quality of the system under test. Let's talk about what quality is. Quality is of value for specific individuals. Quality is the degree to which a component or system satisfies the stated and implied needs of its various stakeholders. Quality is inherently subjective. Different stakeholders will perceive the same product as having different levels of quality. A bug is a discrepancy between expectations and reality. It's an attribute of a software product that reduces its value to the stakeholders or increases its value to, let's say, their competitors, who are more interested in it failing. A bug may or may not be a coding error or a functional error. Design and requirement errors are bugs as well. What's a defect? What's the difference between an error, a defect, and a failure? Computers don't make mistakes. The saying goes to err is human. Errors are resultant of human actions that cause an incorrect outcome. When an error is made, it leads to an introduction of a defect. A defect or a bug is an imperfection or deficiency in the work of a product, something that does not meet its requirements or specifications. Sooner or later, a defect may lead to a failure, an event where we see the consequences of a bug. This is where a component or a system does not perform a required function within specified limits. Let's look at the next example. A human mistakenly thinks that you can represent the meters per second value as a 2-byte variable. So when the speed exceeds a certain limit, all the values that are larger than the said limit will be considered an error. If this value is used to calculate the braking path, then a vehicle can think that its speed is 0, even though its actual speed is 66 to 70 kilometers per hour, which in turn can lead to an accident. The human made an error which brought forth an introduction of a defect. This defect may remain dormant if the car travels at a speed of 65 kilometers per hour or lower. But if the driver accelerates beyond that, it will lead to a failure. A similar problem led to the explosion of the Ariane 5 space rocket, one of the costliest software defects ever. One more example. The fact-checking website Snopes.com features the following urban legend. A complaint was received by the Pontiac division of General Motors. This is the second time I have written to you, and I don't blame you for not replying, because I kind of sounded crazy, but it's a fact that we have a tradition in our family of ice cream for dessert after dinner each night. But the kind of ice cream varies, so every night after we've eaten, the whole family votes on which kind of ice cream we should have, and I drive down to the store to get it. It's also a fact that I recently purchased a new Pontiac, and since then my trips to the store have created a problem. You see, every time I buy vanilla ice cream, when I start back from the store, my car won't start. If I get any other kind of ice cream, the car starts just fine. I want you to know I'm serious about this question, no matter how silly it sounds. What's there about a Pontiac that makes it not start when I get vanilla ice cream and easy to start whenever I get any other kind? The Pontiac president was understandably skeptical about the letter, but sent an engineer to check it out anyway. The latter was surprised to be greeted by a successful, obviously well-educated man in a nice neighborhood. He had arranged to meet the man just after dinner time, so the two hopped into the car and drove to the ice cream store. They got the vanilla ice cream, got back to the car, and sure enough, the car wouldn't start. They later made more trips for chocolate and strawberry flavors, and in both cases, the car started just fine. On the night they got vanilla, the car failed to start. Now, the engineer, being a logical man, refused to believe that this man's car was allergic to vanilla ice cream. He jotted down all sorts of data: time of day, type of gas used, time to drive back and forth, etc. Finally, he had a clue. It took less time to buy vanilla than any other flavor, and the answer was in the layout of the store. Vanilla, being the most popular flavor, was in a separate case at the front of the store for quick pickup. All the other flavors were kept in the back of the store at a different counter, where it took considerably longer to find the flavor and get checked out. So once time and not the ice cream flavor became the problem, the engineer quickly came up with the answer: vapor lock. It happened every night, but the extra time taken to get the other flavors allowed the engine to cool down sufficiently to start. When the man got vanilla, the engine was still too hot for the vapor lock to dissipate. So again, engineers made a mistake. A defect was introduced and frankly could have gone undetected if not for this specific timing and ice cream flavor coincidence. Software testing is searching a program for errors. Software testing is an empirical technical investigation conducted to provide stakeholders with information about the quality of the product or service under test. Every word of this definition matters. It's important that testing is an investigation. It's also important that it's rooted in reality, because we're testing a specific piece of software and we're doing it systematically and technically. Testing is also about providing information. We need to find discrepancies between our stated and implied expectations and reality. It's what we could have had versus what we actually have. Why is testing becoming more and more important in today's world? Sooner or later, our life will be permeated by programs. Little by little, real-life, tangible objects will transform into software programs. Then all aspects of our lives will depend on how well the quality of software satisfies our expectations, as well as how healthy and happy we are. Existential risks can be analyzed. We can see which risks pose more of a threat and which risks show a higher likelihood of occurring. But if we look at the risks that can potentially endanger humanity, many of them will be connected to software. If the software is too smart or not smart enough, it can jeopardize everything important to us. The more we depend on software, the more paramount its quality becomes. From vaccine creation to exploring outer space and natural disaster control, the information about our new computer reality will become increasingly significant. And software testing will, in turn, become one of the most important professions. The connection between software testing and QA is often misunderstood. People confuse testers with QA engineers, but testing is just a part of QA. QA is a multifaceted notion. It includes management of developers, processes, systems, and so on. People erroneously think that a tester can influence all QA-related processes, while a tester should only focus on his or her primary objective, finding defects and reporting them to stakeholders. Michael Bolton gave an excellent presentation called "Testers Get Out of the Quality Assurance Business." It states that if you want to improve the code, then you should become a programmer. If you want to improve the process, then you should become a manager. If you want to test, then you should test. Testing is a critically important aspect, but it's limited to finding information and conveying said information. If you want to be something, you shouldn't be something else. Let's see what else testing is not. First of all, it's not modular testing or unit testing development. Development of unit tests allows you to isolate individual parts of the program and test their performance, creating tests, executing them, and obtaining reports using open source frameworks like PyTest or PyUnit. Unit testing was the topic of workshop 3 of this online course. So, as you might have realized, unit testing is not testing. It's coding, that is writing the system's code, and also code that features tests. Unit tests are not about getting information. They themselves are a part of the system. Quite often, the developers have to write scenarios in Gherkin. Sometimes this is called BDD or behavior-driven development. BDD is a collaborative process of requirements development, usage scenarios, and acceptance testing. BDD is a process of program development, and again, BDD is not testing. Software testing is about exploring the software with the aim of finding defects. If one is occupied with trying to confirm that something works instead, then this is not software testing. So let's get back to our scientist, journalist, and investigator example. Let's say you are a scientist, but you have strong beliefs about how everything works. If all the experiments you conduct never shake your beliefs despite the fact that the outcomes disprove them, then you are not a true scientist. The same goes with journalism, which is about obtaining and delivering accurate information. But if a journalist already has a narrative and bends the facts to fit this narrative, this stops being journalism and becomes propaganda. The same can be said about investigators. On the one hand, they can work hard examining the evidence, trying to understand what happened. But on the other hand, they could have a person in mind that's the most obvious choice or that needs to be convicted for this crime for some reason. So a whole range of that accumulated evidence will be ignored to pursue the idea of convicting that specific person. There's a great movie about software testing called The Pentagon Wars. We have a short review of this movie on our Exactpro Systems YouTube channel. I highly recommend this movie. It shows a sharp contrast between the true and fake testing. Just to summarize, true testing is finding defects via a series of trials, while fake testing is just confirming that something is ready for use. This is when we don't try to subject our system under test to the necessary amount of testing. You can also check out this blog post showing what testing is not. Let's take a look. Testing is not a set of predefined actions. Acquiring information is complex and nuanced. Testing is not breaking the product. Testers don't destroy the product, they destroy the illusion that the product is flawless. Testers don't add new defects to the product. They find the bugs that were added by the developers. We do recommend reading this blog post, even though some statements in it are quite questionable. For example, testing is not finding bugs. That's fundamentally wrong. It's like saying the job of a firefighter is not putting out fires. Firemen do lots of things. They ride a shiny red vehicle, they work out to stay in shape, they check their equipment, they teach safety classes at schools, but the most essential aspect of their job is their ability to extinguish fires. If a firefighter is not putting out fires, then most likely he is not much of a firefighter. The same applies to finding defects in testing. The next thing we're going to discuss is testing principles. The list you see is taken from the ISTQB Foundation level syllabus. Principle 1. Testing shows the presence of defects, but not their absence. Testing is an empirical investigation. To demonstrate the presence of bugs, you have to just find one, but you cannot demonstrate the opposite. The picture shows the situation where one cat tells another one that he checked every square inch of the house and didn't find the mouse. However, the absence of proof is not proof of absence, so the essence of testing is showing that problems exist. Principle 2 states that exhaustive testing is impossible. We cannot check all possible scenarios and execution paths. Even if you take the simplest program, you will quickly notice that the amount of existing combinations is infinite. Look at autonomous vehicles. There's an infinite amount of roads, pedestrians, other transportation, road signs, and combinations of these traffic participants. We cannot possibly foresee all potential scenarios of what can happen on the road, but our goal is to identify the most critical ones. Principle 3 states that early testing saves time and money. The sooner we find out about an impending problem, the more time we have to find an effective solution. Autonomous vehicle simulators, including the one we're using during this course, help us start testing much earlier. We can connect the vehicle stack to the simulator and launch it in a Unity world controlling the car's behavior. We're not conducting our first autonomous vehicle launch in a populated area to find first bugs. The earlier we start this testing process, the more time and money we save. Principle 4. Defects cluster together. It's a representation of the Pareto principle, which aptly points out that everything around us is not distributed evenly. It's more of an 80-20 distribution. For example, 80% of wealth belongs to 20% of people, and vice versa. The majority of stock exchange trades are executed by a handful of instruments. The majority of bugs hide in a small amount of units. This could be explained by the fact that those units were programmed by certain individuals or are of different levels of complexity and/or requirements clarity, etc. So this 80-20 distribution principle can be found in testing. Knowing this principle can help you carefully plan your testing processes. Principle 5. Beware of the pesticide paradox. The paradox states that the insects that survive the first pesticide attack will most probably survive the second one as well. A virus that attacks you once and has your system produce antibodies isn't likely to do much damage the next time you encounter it. Similarly, when we run the same tests over and over, when we use the same approaches of finding defects, then there will be bugs that continuously escape our testing processes. These defects will eventually be resilient to our testing methodology. Imagine that we test our driverless vehicle on the same stretch of the road. The first time we run a simulation, we will find many problems on every turn. But the more we follow the same trajectory, the fewer issues we encounter. Does that mean that our car is ready for real-life testing? Probably not. As soon as we leave the well-trodden path, the problems will tread our way. Principle 6 states that testing is context-dependent. Everything is context-dependent. Humor is context-dependent. Depending on the appropriateness of the context, the same joke can either have the audience bursting in laughter or exchanging glances in awkward silence. The context-driven testing school we mentioned earlier today are avid critics of ISTQB. The school has 7 of its own testing principles that you can see on the screen right now. These are: the value of any practice depends on its context. Number 2 is there are good practices in context, but there are no best practices. Number 3 is people working together are the most important part of any project's context. Number 4 is projects unfold over time in ways that are often not predictable. Number 5 is the product is a solution. If the problem isn't solved, the product doesn't work. Number 6, good software testing is a challenging intellectual process. Number 7, only through judgment and skill, exercised cooperatively throughout the entire project, are we able to do the right things at the right times to effectively test our products. The authors of these principles include James Bach, Brett Petticord, and Cam Kainer. ISTQB listened to their critique, and you can see a new chapter called Context-Driven Testing in the 2018 edition of the syllabus. It says that we should consider software development lifecycle model and project methodologies being used, test levels and test types being considered, product and project risks, the business domain, operational constraints including but not limited to budgets and resources, timescales, complexity, contractual and regulatory requirements, organizational policies and practices, and required internal and external standards. Principle 7 focuses on the absence of errors fallacy. First 2 principles stated that tests can only show the presence of defects and that testing cannot be exhaustive. So if we think that there are no more bugs, then we are wrong. Even if we checked all the requirements and the system behaves as expected, it doesn't mean that there are no more defects in the system. The system always has bugs. The ISTQB syllabus draws a line between verification and validation. According to its glossary, verification checks whether the system meets specified requirements, while validation checks whether the system satisfies user or other stakeholder needs. Let's look at the example. Here you see a Volvo car that Uber used to test their autonomous driving system. The damage you witness here is the result of an infamous accident that the car got into. This marked the first time a driverless car ran over a pedestrian. There's an official report describing how the accident happened. You can follow the link and check it out. According to the data obtained from the self-driving system, the system first registered radar and LiDAR observations of the pedestrian about 6 seconds before impact, when the vehicle was traveling at 43 miles per hour. As the vehicle and the pedestrian paths converged, the self-driving system software classified the pedestrian as an unknown object, as a vehicle, and then as a bicycle with varying expectations of the future travel path. Since all of those objects could potentially move with different speeds, the predictions varied. The pedestrian was walking with his bike next to him. At 1.3 seconds before impact, the self-driving system determined that an emergency braking maneuver was needed to mitigate a collision. According to Uber, emergency braking maneuvers are not enabled while the vehicle is under computer's control, to reduce the potential for erratic vehicle behavior. So in this case, the verification passed and the system met all the specified requirements. The validation, on the other hand, came up lacking because the most crucial requirement in a situation like this would be to hit the brakes. Let's now move on to the test types. Testing can look for deviations from functional requirements as well as from non-functional ones. Functional testing answers the question of what. We look at what software does and we find defects. During non-functional testing, we check if the software complies with certain characteristics. Here, we try to answer the question of how. How does the software do it? This includes the program's capabilities to handle various loads, transfers from one environment to another, as well as security, efficiency, etc. Exactpro's experience suggests that the line between functional and non-functional testing is blurred. It's not only the question of what the software does that's important to us, but also how it does it. What without how is quite boring. And again, if you apply this to autonomous vehicle systems, we'll see that the fact that they can process the information means very little if they don't do it fast enough. Real testing happens at the confluence of functionality and technical characteristics. You can also differentiate between the types of testing by how familiar you are with the code structure. One of the test types here is testing with access to the program's structure. It's called Whitebox or glass box testing. Here, we not only use what is on the outside, specifications, requirements, and expectations, but also leverage the access to the software structure, architecture, settings, and so on. This helps us understand how our search for defects reflects on the inner workings and code of the program. There's a catch here, though. When we know too much, we make additional assumptions. That's why simple black box testing is quite useful because not being exposed to the code lets us avoid making cognitive mistakes its developers made. We simply review the program as a black box. Moving on to testing components. As we've mentioned before, the foundation of testing rests upon processes, platforms, and people. Platforms or tools will be the subject of our next lecture. So now we will discuss processes. What do they include? They include test planning, which involves defining the objectives of testing and the approach for meeting those objectives within project constraints and contexts. They also include test monitoring and control, which compares actual progress against the plan, takes actions that are necessary to meet the mission objectives of the project, and/or adjust the plan. Test analysis determines what to test. The testing process has to be grounded in reality. The test object needs to be real, and we have to analyze it beforehand. Test design addresses the question of how to test. Test implementation asks, do we now have everything in place to run the tests? Test execution runs tests. This is where we do our empirical research. Test completion summarizes the results of testing. Very often, many of these processes happen simultaneously, producing different reports, scenarios, test results, logs, and bug reports. Now, what are the main test objectives? The list you see here is taken from the ISTQB syllabus. Of course, it does raise some questions. There is and should only be one objective: to find the discrepancies between the expectations and reality. However, this list puts it at number 5. Meanwhile, number 1 states the following objective: to prevent defects by evaluating work products such as requirements, user stories, design, and code. It's important to know that bugs are introduced not only during the coding process, but during any product lifecycle stage. The discrepancies between expectations and reality can happen at any time. The investigation of all stages is just as crucial as testing the program itself. And it's not different from testing, it's still an empirical and technical research process, so finding bugs and avoiding bugs is the same. Objective 2 states, to verify whether all specified requirements have been fulfilled. We've already mentioned that exhaustive testing is unachievable, which means it's impossible to check all the requirements. Whether the goal of testing is mindless box checking of the specified requirements is quite questionable. The same goes to point 3. To check whether the test object is complete and validate if it works as the users and other stakeholders expect. Again, since exhaustive testing is impossible, we cannot be 100% sure that the test object is complete. Testing has to find bugs and not to claim that the test object doesn't have any. Objective 4 is to build confidence in the level of quality of the test object. Now, this is interesting. As we have mentioned before, testing is an information service. It provides information about software. If it's useful and plays to the stakeholders' strengths, then it will start to build confidence. If the information is chaotic and useless, then it will create nothing but mistrust. During the online seminar entitled The Impact of AI on Software Testing, one of the topics discussed was science. The mutual consensus seemed to be that science is good and not accepting that it's bad. Some of the statements that were bounced around included the idea that Donald Trump didn't get his second term because of science. But they also talked about the fact that science evolves. That's why some people choose not to trust it. The same can be said about testing. Since we cannot guarantee exhaustive testing, then it can mean that what we know today can become irrelevant tomorrow. Older problems can disappear and the new ones arise. Let's take wearing masks as an example. At some point at the beginning of the pandemic, Center of Disease Control's Anthony Fauci appeared on TV, and he was adamant that there's no need to be wearing masks unless you're sick or you are a medical worker. In the same interview, he added that the mask-buying mass hysteria can create a shortage of masks for medical workers. Later, he changed his opinion, saying that masks are important for everyone. After some time passed, he added that wearing 2 masks is even better. You can see that this can certainly create a level of mistrust in people who promote science. So you should make sure that those who provide you with information don't have ulterior motives. If a tester doesn't see that his or her primary objective is to provide honest information, but sees it as an opportunity to influence the stakeholders' decisions, then the trust in this kind of testing will diminish. And trust is essential here. And for it to remain the cornerstone of the process, testers need to fulfill their primary purpose, finding defects and honestly reporting them to the stakeholders. The rest is self-explanatory. Objective 5 is to find defects and failures, thus reducing the levels of risk of inadequate software quality. Objective 6 is to provide sufficient information to stakeholders to allow them to make informed decisions, especially regarding the level of quality of the test object. The 7th and final objective is to comply with contractual, legal, or regulatory requirements or standards, and or to verify the test object's compliance with such requirements or standards. Now let's visit the Autonomous Vehicle Contest website and see the acceptance criteria. There are 4 of them. So a part of your grade is a successful launch of test scenarios using scripts. So here they check if we actually managed to test something. If you did, you were halfway there. If you tested it under various conditions and on different trip routes, that's even better. The second criterion is automation. If half of your tests are semi-automatic, then your grade is 70 to 80%. And if all tests are automatically executed and validated, then your grade jumps up to 96 to 100%. Next criterion. You can get a 20% grade increase if you detected problems in the simulation. If you found just 1, they mark it fair, but if you found more than 5, the grade is very good. And if you found more than K issues, that's excellent. The last one evaluates your presentation, where you can get up to a 10% bump in your grade. So why is this table fascinating? It shows us how people evaluate the quality of testing. Of course, the numbers we see here are debatable. Everybody has their own idea of what good testing is. Let me reiterate. Testing is processes, platforms, and people. The last component is people. Let's try answering a question. Is it the tester's fault that we have a bug in production? Early on, we talked about the difference between testing and QA. A tester is not responsible for hiring developers and managers, for whatever is going on in the IT department or what business analysts do. So a tester cannot assess the quality. What does that mean? Is it his or her fault? Our opinion is absolutely yes. We are trying to train good testers. True software testers should have a sense of responsibility. They have one task and one task only to find information about issues. If they fail to do so, it means that they did a bad job. If you teach your testers that quality is a mutual responsibility, then they will always try to find a way to blame somebody else. For example, someone else didn't explain it to me, or I didn't get the full explanation from someone else. We're basically training testing Navy SEALs. There's a book that we highly recommend called Extreme Ownership. A lot of ideas mentioned there can be applied to software testing. We teach our testers that their sole responsibility is to find bugs and to make sure that none of the defects pop up after going live. And that happening is nobody else's fault. At Exactpro, we teach 7 principles of good testing. I mentioned the first one already. It's ownership. It's something that you cannot be given. It's something that you take. The second one is deep impact. Testing is an information service, and information has no value unless it's being used. Only something that we can use has value. The information we uncover is important to others. The more influence this information has, the more valuable it is. Our logo says, Exitus acta probat. The outcome justifies the effort. The result is the criteria of your work. If your testing doesn't find any defects, then you are doing it wrong. If your testing doesn't produce any information valuable for stakeholders, then you're doing it wrong. Make sure that your work results are a valuable contribution. If you want to go fast, go alone. If you want to go far, go together. Now, the next principle is hard work. Nothing of value is produced without effort. It also applies to software testing. Good testing requires a lot of effort. The next one is software testing is relentless learning. Change is the end result of all true testing. If testing teaches us nothing, then it's not good testing. The next principle is agility. The only constant is change. If the way you test does not respond to the changes around you, then it's not worth a thing. The next principle is communications. We don't need some insider knowledge. We need information that can become the basis for making decisions and taking action. The ability to explain and understand is paramount. The last principle we teach is objectivity. Ray Dalio says it in his book that you have nothing to fear from knowing the truth. When you test, you receive information. If this information is not objective, if it has other motives, then it's bad software testing. If you have any comments, observations, or objections, please let us know in the comments below. We will try to address them as best we can. At this, we wrap up for today. Feel free to like this video and subscribe to our channel for all things software testing. Have a good day and goodbye!